Hello everyone. In this lesson, I am going to discuss about the nature of bonding in organic molecules. You know that when you consider an organic molecules are the molecules which going to contain carbon, hydrogen and oxygen as major elements. Along with that, you may also have sulfur, halogen, phosphorus and also metals. So you should be able to understand the nature of bonding, how the bonding is taking place. Bonding is nothing but the force of attraction between the elements of that particular compound, that we are going to call it as the bonding. So when you consider the organic molecules are formed generally by covalent bond. Covalent bond is nothing but according to the valence bond theory, there are many theories are there to explain the covalent bond. One of the theories which successfully explain the formation of covalent bond is valence bond theory. According to valence bond theory, the mutual sharing of electrons lead to the formation of the covalent bond. Once the covalent bond is there, how the mutual sharing taking place, that depends upon the types of overlapping, how the overlapping is taking place. There are head-on collision and also sideways collision are there. So what type of overlapping is taking place? Are complete overlapping, partial overlapping, that leads to sigma and pi bonds in a chemical bond, that you are going to study in this chapter. Another important concept that you have to understand when you consider the unsaturated molecule which going to contain a double or a triple bond, or it going to have a conjugation, that is called as resonance. So in the resonance, we are going to write the arrow mark that indicates the movement of electrons towards one atom or away from the atom. So it may be a curly arrows, formal charges, double-sided arrowhead, single-sided arrowhead. So many representations we are going to do while writing the reaction mechanism, while considering the transfer of electron from one atom to another atom. So all those things with respect to resonance you are going to study in this chapter. Along with that, you are also going to understand localized and delocalized chemical bonds. When you consider the aromatic compounds, there you come across localized and delocalized, are the compounds which going to have an unsaturation, having a double bond in conjugation. So you come across that. Similarly, conjugation, non-conjugation, cross-conjugation chemical bonds, these are the various types of bonds you come across in organic chemistry. You are going to study, you are going to understand, you'd be able to differentiate between localized, delocalized, conjugation, cross conjugation, no conjugation, covalent bond, what type of movement of electrons is taking place, everything you are going to this lesson. So I told you there are different theories are that put forth in order to understand the covalent bond. The first theory was Lewis concept. So covalent bond is formed by, according to this concept, the covalent bond is formed by sharing of electrons. Depending upon the number of electrons shared by each atom in a bond formation, single, double or triple bond may be formed. For example, we have taken a simple example of water. In water, you are going to have 2 hydrogen and 1 oxygen. So you have to consider the valence electrons. We have to consider the electrons which are present in the outermost shell. So in the oxygen, when you consider the outermost shell, based on their electronic configuration, you are going to have 6 electrons. So in order to complete the octet, you require 8 electrons. Therefore, it going to take 2 electrons from the 2 hydrogen atoms. Thereby, it going to form a bond between 2 hydrogen to form water. Thereby, even hydrogen also will going to have an octet arrangement. Oxygen also will going to have the octet arrangement. Whenever the chemical bond takes place, they tend to become electrically low energy, or they try to be having the octet arrangement. So here, by losing by giving the electron, by sharing the electron, hydrogen also will going to have the octet configuration. Oxygen by taking also it going to have the, it also going to share, it also going to have the octet arrangement. This is the way you are going to get. Since only one atom is shared between them, they're going to form a single bond. But when you consider the carbon dioxide, formation of carbon dioxide, you are going to have 1 carbon, 2 oxygen. Here carbon has how many valence electron? 4 valence electron. Whereas oxygen will going to have 6 valence electron. So in oxygen, in order to have the octet arrangement, it should have 2 more electrons. So each oxygen will going to contribute, will going to share the two electrons, and each atom also going to, because it has only 4 electrons, it require another 4 electrons to have the octet arrangement, thereby it going to share its electron with the oxygen. Since two pair of electrons are taking place between carbon and oxygen, two bonds are formed. So depending upon the number of electrons shared by each atom, the different types of bond you are going to get. If only one electron is shared, then you are going to get a single bond. Two electrons are shared, then you are going to get a double bond. We will take the example of N2, formation of N2 or N plus N. Again, nitrogen will going to have, one nitrogen will going to have 7 electron, another nitrogen will going to have 7 electron. By sharing 3 pair of electrons, so they are going to form a triple bond. This is the concept explained by the Lewis concept. The covalent bond is formed by sharing of electrons. But later we are going to have valence bond theory, VBT. Here it says that it's not only the valence electron which are present in the outermost shell, they have to overlap with each other, having off-filled valence electron, then only the chemical reaction takes place, otherwise there won't be any chemical reaction. This is according to valence bond theory. So here the concept of overlapping will come. So the valence electrons are there, two different atoms are there, they have to overlap with each other, they have to overlap with the atomic orbital having off filled, which going to have the unpaired electron. They are going to combine together, they are going to overlap with each other, they are going to interact with each other to form the bond. So for example, when you consider the hydrogen, it going to have only one electron, therefore 1s1, it going to have s orbital will be in a spherical shape. Another hydrogen also spherical shape, they have to interact with each other, they have to overlap with each other, then only there will be a formation of this is according to valence bond theory. So when you consider the overlapping may be in two different ways. One is called as axial or head-on or end-to-end overlapping. Other one is called as lateral or sideways or parallel overlapping. So depending on the type of overlapping, different types of bond will be formed in organic chemistry. Axial or head-on or end-to-end overlapping, when you consider, that leads to sigma bond. Here the covalent bond is formed. You know that bond is formed when you have the valence electron, and those valence electrons should have unpaired electron. They have to overlap, then only the covalent bond is formed. How the overlapping is taking place? The overlapping is taking place, complete overlapping or end-to-end overlapping is taking place. It is called as axial overlapping. So that leads to bond, and that bond we are going to designate it as sigma bond. So here the overlapping between S and S overlapping may be there, or S and P orbital can overlap, and P and P overlapping, all these three overlapping leads to sigma bond. Again, depending upon the valence electron, whether the valence electron present in the S orbital, whether the valence electron present in the P orbital, depending upon that, different types of overlapping will take place. Each atomic orbital, if it is a S spherical, P means dumbbell. So different types of shapes are there, that leads to complete that leads to axial head-on end-to-end overlapping. That type of overlapping we are going to call it as sigma bond. For example, when you consider the S orbitals having S electrons in their outermost shell, having the unpaired electron, when they combine, when they overlap, you are going to get a sigma bond. Complete overlapping is taking place. That is the way you are going to get the sigma bond. Similarly, the S, because the atoms which are involved in chemical bonding, they may be present, one atom is present in S orbital, another outermost electron present in P orbital, then also overlapping takes place between S and P, and that also leads to sigma bond. Here also axial overlapping, maximum overlapping is taking place to form the sigma bond. Similarly, the atoms which are involved in a covalent bond, if they are present in the P orbital, again P orbital overlapping will be there, P orbital will be dumbbell in shape. Here also complete maximum overlapping is taking place to form the sigma bond. So this is the way in organic chemistry you come across two different types of bonds. One is called as a sigma bond, other one is called as the bond. Sigma bond means axial head-on Whereas when you consider the pi bond, that is sideways or lateral overlapping, not complete overlapping. This is a weak overlapping. So only at this side, because I told you p orbital is dumbbell in shape, therefore it may takes place a sideways or a head-on. Head-on means maximum overlapping takes place. Sideways means minimum overlapping takes place. Maximum overlapping leads to a stronger bond. Minimum overlapping gives to the weaker bond. Therefore, pi bonds are weaker compared to that of sigma bond. But in organic chemistry, depending upon the type of the valence electron, depending upon the atomic orbital present in the outermost shell, so different types of bond overlapping leads to different types of bond. One is a sigma bond, other one is the pi bond. When you consider the sigma bond, the bond is formed by the axial overlapping of atomic orbital, that we are going to call it as a sigma bond. But here sideways overlapping, that leads to pi bond. Here sigma bond is quite large and bond is strong, because I told you the maximum overlapping is taking place in sigma bond, therefore that is stronger bond. When you consider the pi bond, the overlapping is less and the bond is weak. S orbital can take part in the sigma bond formation. S orbital do not take part in pi bond formation. Only the one lobe of the p orbital is involved in overlapping. When you consider the sp overlapping or pp overlapping, all the lobes are not involved in the sigma bond. Only one lobe of the p orbital will be involved in overlapping. When you consider the pi bond, both the lobes of the p orbital are involved in the overlapping. Even though both the lobes are involved, since the overlapping is not very strong, not completely, therefore that bond is very weak. The bond can be formed even in the absence of a pi bond, whereas a pi bond cannot be formed in the absence of a sigma bond. Then here free rotation of the atom around the sigma bond is available, whereas a free rotation is not available in the case of the pi bond. Again, type of, depending upon the type of bond, so that different chemical reactions, different chemical mechanism may takes place, that leads to different energy pattern, that leads to different velocity at the rate of the reaction. Therefore, it is necessary to understand whether that a sigma bond is involved or pi bond is involved in a chemical reaction. This is one way of understanding the chemical bond. And also, once the chemical is bond, once a reaction has to take place, there should be migration of electrons from one atom to another atom. The electron has to move. If your molecule is neutral, it doesn't take part in chemical bonding. It should have some polarity. It should have some highly negatively charged or positively charged poles. It should have two poles. It should have some sort of polarity in the molecule. Then only the chemical reaction takes place. The movement of electrons in an organic reaction, we are going to write in the form of the curved arrow. In the form of a curved arrow, we are going to represent that, going to show how the bond is taking place, how the bond is breaking, whether the electrons are moving towards which atom. Everything you are going to understand by the movement of electrons. How the movement of electrons are taking place, we are going to write in presence of the curved arrow. The double-headed arrow mark indicates the flow of two electrons. Single-headed or fish hook arrow indicates the flow of one electron. How the electrons are moving from one atom to another atom, how the electron pair is shifting, that can be indicated the curved arrow. For example, when you consider the double bond, so double bond going to contain a pi bond. So that pi bond to adjacent bond, it has been moving. So we are going to write like that. The pi bond to the adjacent atom. Again, two bonds are there, that also may undergo. Like that, there will be a movement of electron from atom to another atom. The double-sided arrowhead and also single-sided arrowhead, that also you are going to come across. Curved arrows used to indicate the movement of electron. Regular arrow, double-sided arrowhead used to indicate the movement of two electrons. A line with a single sided arrowhead, sometimes also called as a fish hook arrow, used it for single electron movement in the with a radical single electron movement you come across. So these indications are very important in order to the chemical reaction. Similarly, three electron pushing arrow moves are also there. See, this is the way they are going to show the movement. So you are going to have 1, 2, 3 carbon atom. So from carbon atom 1 to 2 is moving. Thereby we are going to show the arrow mark with a double sided arrow mark. 2 electrons are moving. That's the way. Similarly, the lone pair of electron can also be moved into a product. It's a reverse of that can also be taking place. Pi bond to pi bond is also possible. Sigma bond to pi bond is also possible. Lone pair to pi bond is also possible. Like this, different types of movement of electrons will take place that I'm going to write in the form of the arrow mark. The correct way of moving the electrons we have to represent, but not the otherwise. So you have to know how the movement of electron is taking place from pi to unsaturated electrons or to lone pair of electron or lone pair of electron to this. That is very important. Therefore, the movement of electron, how we are going to represent the arrow mark, that's also a very important matter. Ionic reaction mechanism. Breaking the bond can create relatively stable ions. How the breaking takes place? From which side the breaking is taking place? Because there are so many reactants are there where exactly the breaking is taking place. So that can be easily represented by these things. Similarly, we come across another important concept in the unsaturated compound having a single and a double bond. That we are going to call it as a conjugation. That phenomenon is called as resonance. In the case of a single bonded molecule, just the movement of electron will take place, but also in the case of the closed aromatic ring-like structure, which is going to have an alternative single and a double bond, they are going to have a special phenomena, and that phenomena is called as a resonance. So resonance structures are the alternative to Lewis structure, but not the same. They are the alternative structures. So for the simple molecule, I can write many resonating structure, but each time I cannot write the resonating structure which is the resultant of many resonating structure. For example, when you consider a benzene, I can write 8 different resonating structure. All 8 resonating structure I am going to add together. Resultant of all 8 structure I am going to make it as a one structure for convenience to write on the paper or on the board. That I am going to call it as the resonance hybrid. The properties of the covalent molecule species that could not be represented by a single structure, that we are going to call it resonance. Resonance has a pronounced influence on structure, chemical reaction and also physical properties. So when you are studying the reaction mechanism, when you are studying the given reactant, what type of reaction that may undergo, what type of cleavage it may undergo. So that depends upon the starting material. If your starting material is a resonance hybrid, then it's going to have different physical properties and chemical properties, the rate of the reaction, so many parameters will be involved in understanding the reaction pertain to that particular reactant. The resonance structures do not have a real existence as an individual species. They are imaginary structure proposed to explain the properties of the molecule. None of these resonating structure can be prepared in the laboratory in real sense. The resonance hybrid is the real structure. So it is the equivalent, which is a resultant of all the structures. We are going to take one structure, that is a real structure. Resonance energy is defined as the energy difference between the most stable resonating structure and the resonance hybrid structure. Here also we come across one more parameter in order to understand the resonance, that is resonance energy. Each structure will going to have its own energy and also resonance hybrid. The difference between the energy of the resonating structure and resonance hybrid, that we are going to call it as the resonance energy. Greater the resonating energy, greater is the stability of the molecule. The resonance hybrid has a lower energy, thus its greater stability than any of the contributing structures. So, resonance hybrid and resonance structures we play a very important role. Resonance exists only in those part of the molecule which are composed of sp or sp2. This is possible only in case of unsaturated hydrocarbons having triple or a double bond. Sp means a triple bond, sp2 means it is a double bonded. The p orbitals are in absolute requirement for resonance since they do not contain any sp3 hybridized atom. So all the atoms in a molecule taking part in resonance should be coplanar. This is necessary for effective overlapping of p orbitals. So when the resonance takes place, only it is possible with the overlapping of p orbital. Then only it is possible. Otherwise, it is not possible. For the resonating structure, the position of the nuclei must be in the same in all the structures, and total charge should be constant. Here when I am telling you that all the resonating structures are equivalent. They are going to contain the same number of electrons, and also they are going to contain the same energy, almost same energy. Total number of charges remains the same. So if all those things are there, then only we are going to consider they are not two different structures, but they are the same structure. They are the resonating structure. All the resonating structure must have the same number of unpaired electron, and also they should have total charge must be same, must be constant in all these structures. Resonance structures with a greater number of covalent bonds are more stable. In resonance structure, the electrons move between the adjacent atom, that is a lone pair or pi electrons are negatively charged, or unpaired electron present on radical are moved. Just they keep on moving from one atom to another atom. Resonance donor atom, when you write the arrow mark, you are going to consider resonance donor atom move to the resonance acceptor atom, which must be adjacent to the donor atom. Then only it is possible, otherwise it's not possible. Here I have given a example in which you are going to have a lone pair on the carbon, which is called as resonance donor. Other one we are going to have a resonance acceptor, that is carbon, which is going to have the positive charge. Negatively charged means they are electron rich. Positively charged means they are electron deficient. The curved arrow indicates the shift of electron pair. So this is the way it going to takes place. So all these indications, all these representations we are going to do while doing the reaction mechanism, while understanding the reaction. Therefore, these are very important in case of unsaturated hydrocarbons. Similarly, we come across another important concept as localized and delocalized chemical bonds. So when you consider a chemical bond, the chemical bond is taking place between two atoms. It's some sort of electrostatic force of attraction is there, that is due to overlapping of the molecules. That sort of bond has been created. So those two bonds are there. One is called as localized, other one is called as delocalized. Localized chemical bonds are the normal molecular orbital overlapping, such as sigma and pi bond. That is called as localized within the local. So they are going to overlap with each other. That's why they are called as localized between the two local atoms. Delocalized chemical bonds are the chemical bonds which are not associated with only one single atom, but with several atom and other chemical bonds. Delocalization occur in case of conjugated pi system. You are going to have a huge number of molecule having different arrangement of atom, and when you consider the chemical bond that has been formed, that has been changing, transferring the electron, that is not between the two adjacent atom. If it is between two adjacent atom, we are going to call it as localized chemical bond. Between the 3 or 4th carbon atom, then we are going to call it as the delocalized. They are not associated through a single bond. They are being associated with a several atom. Such type of bonds we are going to call it as localized chemical bonds. And similarly, delocalization of electrons also takes place. For example, when you consider a benzene, benzene has 3 single bonds and 3 double bonds in the alternating pattern. Where single bond, double bond, single bond, double bond, like that you are going to have the arrangement of electron in benzene. Each carbon atom in its ring has a p orbital that undergoes sideways overlapping. This kind of overlapping is called as delocalization. These electrons are free to move throughout the molecule because they do not have a permanent binding to a single atom or a covalent bond. So such electrons we are going to call it as delocalized electrons. These delocalized electrons play a very important bond. Sigma bond means axial head-on, whereas when you consider the pi bond, that is sideways or lateral overlapping, not complete overlapping. This is a weak overlapping. So only at this side, because I told you p orbital is dumbbell in shape, therefore it may takes place sideways or head-on. Head-on means maximum overlapping takes place, sideways means minimum overlapping takes place. Maximum overlapping leads to a stronger bond, minimum overlapping gives to the weaker bond. Therefore, pi bonds. So this is a way you can understand whether it's a localized bond or delocalized bond. Similarly, another type of chemical bond we come across in organic chemistry, it is called as conjugation or cross conjugation chemical bonds. Conjugation is the overlap of one p orbital with another trans in intertwining a sigma bond. In a larger atoms of d orbital can also be involved. This we are going to call it as conjugation. 1,3-butadiene is an example for alternative single and a double bond. Conjugation. When you have an alternative single and a double bond, that we are going to call it as a conjugation. It's an overlapping of one p orbital with another p orbital which are involving in the sigma bond. So such type of bonding we are going to sigma bond. For example, when you consider the s orbitals having s electrons in their outermost shell, having the unpaired electron, when they combine, when they overlap, you are going to get a sigma bond. Complete overlapping is taking place. That is the way you are going to get the sigma bond. Similarly, the S, because the atoms which are involved in chemical bonding, they may be present, one atom is present in S orbital, another outermost electron present in P orbital, then also overlapping takes place between S and P, and that also leads to sigma bond. Here also axial overlapping, maximum overlapping is taking place to form the sigma bond. Similarly, the atoms which are involved in a covalent bond, if they are present in the dienes. Again, when you consider I told you these delocalization or conjugation play a very important role. So when you consider the stability of these dienes, ethene which going to contain only one double bond, butadiene which going to contain two double bond, hexatriene which going to contain three double bond, oxatetraene will going to contain four double bond. So as the number of double bond increases, the energy of excitation from lower energy to higher energy will decrease. Thereby, the stability increases. So here stability and energy, they are inversely proportional. Lower the energy, higher the stability. Therefore, octatetraene as shown in the picture, they are going to have lesser energy. Therefore, that is more stable. So these things you can also, it will be useful in when you are going to study the higher concepts of spectroscopy. There also you come across this type of conjugation. So amount of energy required to show the excitation, show the formation, show the transition or the promotion from lower energy to higher energy level decreases with the increase in conjugation. That decreases the energy, thereby they are going to have different colors. Diphenyl polyenes have given an example. If n is equal to 1, it is colorless. N is equal to 2 to 4, it is going to have yellow color. N is 5, it is going to have an orange. And n is equal to 8, it is going to have red color. So all these appear in the visible region. As the number increases, conjugation increases, energy decreases, thereby they are going to exhibit different color. They are going to appear in a different colored region. Again, cross conjugation is also another term we are going to use. Here we come across three double bonds. Whereas in the case of conjugated, you come across single bond, single bond, double bond like that. Here also you are going to have a three double bonds which going to have an alternative single and double bond. But when you consider the third one is not in conjugation with the first one, that type of chemical bonding we are going to call it as a cross conjugation chemical bonding. In a cross conjugated compound, three groups are present, two of which are not conjugated with each other, although each is in conjugation with the third one. First, second and third one are in conjugation, but first one and third one, they are not in conjugation. Such type of conjugated bonds we are going to call it as cross conjugation chemical bonds. So you come across in the case of first example, it's an alternative single and a double bond, so that is conjugation. Second one is cross conjugation. You are going to have three double bonds. And third example is non-conjugation. Like this, you come across different types of conjugated bonds in a chemical bond. Cross-conjugated double bond has slightly larger bond length than non-cross conjugated dienes. So therefore, all these type of bond going to affect the rate of the reaction, the path of the reaction, mechanism of reaction. Therefore, it is necessary to understand what type of bonding is involved in a given chemical molecule which undergoes chemical reaction. Thank you. All the best. Remember, carbon has only 4 bonds.